All right, I'm here. I'm here. I'm here. I see your message. You still here? You know, I I commented. I made a comment on your homework assignment and I handed it back. Do you read comments? Well, the comment I made was that hold on, let me get my sketch pad. Where's my writing utensil? Give me a second. All right. The comment I made was if you have point and you got 0.004 amps. But the answer choices were in milliamps. So you had to convert this amp unit into a milliamp unit. And you know that 1 ampere has 1,000 milliamps. So what you're gonna do here, well, 0.004 amps is gonna have how much milliamps? So you're gonna multiply this number by 1,000. So 0.004 times 1,000 gives you 4 milliamps. And so that would be an answer. That would be how you answer number 5 as well. And so it's that's how you would answer that. You understand? How's that for you? Yeah, most likely. I did comment as such. Yo, what the hell? Yeah, I come back and I see this chat. Oh, that's Riha, of course. Yeah, I'm here. I think I am. Can you guys hear me? I think from the future, I'm probably just gonna say I'm starting at a certain time, but then I'm gonna I'm gonna start like 10 minutes later. Should be really low. You guys probably have the delay on the stream should be really low. If it's not low, I would press the live button. That took me 4 seconds when I wrote the one. So I saw myself writing one in like 4 seconds later. I don't know how fast if you wanna maybe decrease your internet speed to load it faster, up to you guys. But for me, it's 4 second delays. Hola, ¿cómo estás? Today's lesson is about resistivity through a wire, through a current carrying wire. Hola, mis amigos. Oh, wait, no, you guys aren't my friends. All right, Joko. What's the word? What's the Spanish word for students? Students. Hold on, let me Google translate this. Oh, hola, estudiantes. That couldn't be more simple. Wait, I thought you're in French. How do I say hello in French? Um, uh, oui, oui, oui. Bonjour. Oh, yeah, bonjour. Yeah, yeah, bonjour. I'm sorry. Huh? Comment ça va? Who's H the Prince, by the way? I've been wondering for a long time now. Who's H the Prince? I don't think I have a student that starts with H in his name. Oh, Hamza. Alright, my bad. I'm sorry. I am good. I thought you were like Dark Knight Gaming yesterday. Weren't you Dark Knight Gaming? You changed it. Good for you. Can you change it to your actual name? That's an old one. That's a really old one. Too bad they're never gonna make more seasons of it. I think there's a movie, and then there's no more. Oh, there's a prequel. The movie was a prequel. I've watched more anime than you guys, trust me. If that's all it takes to become your favorite teacher, I don't want to be your favorite teacher. I haven't watched Akira. No, I have not watched Akira. I'll bet my job, Joshua. Alright, let's get started. It is 2:10. The viewership just drops every day. Uh, Hopefully the people who don't watch the lesson videos though. I do want them to complete the homework. And I think my class is the least amount of work to do, I think, because I literally only have you guys complete homework questions. I don't. Hopefully you guys are reading my comments on your homework questions too, because I correct you if you did something wrong. Hopefully you do that. I mean, I have to change the times because I mean it's probably gonna be 12:30 from now on, or 12 to 12:30. The only reason why I had 12 to, I couldn't do at 12 or 12:30 today was because of a meeting with the science department. Anyway, let's talk about resistivity of wires. I'll start talking after you guys stop talking about anime. I'll move on, right? I am letting you guys take a picture. Did I tell you? I let you guys do. Some of my students do take pictures. Oh, you're saying at least you let us take. Yeah, yeah, yeah. I'm sorry, I misunderstood what you said. All right, let's get started. So, resistivity of wires. So, we're actually going to be talking about this today. I want to go into a quick review of yesterday. I mean, I think you all were here yesterday, except maybe a few of you. But I want to do a quick review first, okay? Now, and I want to make that analogy to electric current again. Like, you have flowing water current is electric current. So, if you have a high moving water current, you can think of it as a high moving electric current, and instead of water, you can think of electrons. Okay, so a high electric current, a lot of electrons are moving uh, over a period of time, And then low electric current, low amount of electrons moving at it over a period of time. And so now there's a ignore the GIF on the bottom, right? Just ignore that. It, actually, hold on. All right, perfect. So let's look at the this picture right here. So again, I want to make an analogy to voltage and resistance. Now, your voltage, and you can kind of think of voltage as a high water pressure. So if you have a lot of water, you have a lot of water pressure. So if you have a high voltage, you have a lot of electrons. And on the bottom left, if you have less water, you have lower water pressure. So if you have lower voltage, you have less electrons. And so what's going to happen is that the high voltage water, or rather high voltage area, is going to push electrons to the lower voltage area. Because again, if there's more water on the top, naturally the water wants to even out. The water wants to go to the area with less water, right? But and that by itself causes an electric current. So when you have more electrons here and less electrons on the other side, what happens is that electrons want to repel each other. Since electrons want to repel each other, they want to get as far away from each other as possible. And what's going to happen is that the electrons are going to start moving to the area with less electrons. And this movement of electrons is electricity. That's how electricity is generated. So this voltage difference causes an electric current. So this drives an electric current through like a refrigerator, through an air conditioner, anything that requires electricity. So that's how electricity is generated. Now, resistance, and again, I only talked about voltage. I want to talk about resistance now. So resistance is if you run electricity through anything, the electrons are going to slow down. And you can think of resistance as this dam, or an appliance as this dam. So let's say a refrigerator is this dam right here. What the refrigerator is doing is, as the electrons are moving through uh, the refrigerator is slowing down the flow of electrons. It's causing a resistance. So if this dam wasn't here, all these electrons would move down really quickly. But because there is a dam here, you are running electrons through, like maybe a refrigerator, maybe a computer, you're slowing down the electrons. And so that's what resistance is. Anything that you run electrons through, there's resistance. You slow down the rate of electrons. And we talked about circuits yesterday, but now I want to talk about wires, circuits and wires. So let's ignore the GIF on the top for now. Let's actually focus on the yellow circuit on the bottom. So electrons are carried through wires, right? And so if you take a look outside right now, you should see on the telephone line, well, I think they're called telephone poles, whatever electricity poles they are, you see those wires on top of the streets. Those are wires are carrying electricity, right? Those wires are carrying electrons. And as electrons flow through whatever wire they have, that wire, those electrons are bouncing all over the place. And so the material themselves causes a resistance. Just the act of electrons flowing through a material, there's a resistance on those electrons because of that material. And so that's the main focus of today. How do we calculate resistivity of what is the resistance something experiences when electrons flow through a material? All right, again, this is a simple circuit. This is a simple circuit right here. So you have a battery, the long-headed symbol, the long line symbol, that's your positive side. The short side is your negative side. And so the electrons go from the negative side to the positive side. And so this resistor right here is anything that uses electricity. Could be your phone, could be your Nintendo Switch, could be your Xbox. Those are all resistors. Anything that has electrons going through it is a resistor. All right. Now, and the resistor will cause resistance. But as the electrons are flowing through the circuit itself, as it's flowing through the circuit, this circuit is slowing down the flow of electrons. It doesn't want these electrons flowing through them, but they are. And so the formula for that is calculated using this, right? So R is equal to PL over A. It's not exactly a P, it's like a special P. I forgot what the name of it was, but whatever. R is equal to PL over A. So R is your resistance, L is your length of the circuit wire. So if you take a look up here, the length is the length of the circuit wire. A is your cross-sectional area. A is the area of the circle right here, and length is length. Not sure how else to describe it. And P is your resistivity constant. This is on your reference table. So if you look at your reference table, probably maybe I forgot what page it was, but it's definitely on your reference table. This is what you should see. So each of these materials, whatever wire it's made up of, if it's made up of aluminum wire, copper wire, gold wire, nichrome, electrons travel through them at different speeds, at different temperatures. Okay. So depending on the material, electrons can travel slower or faster. Rho, right? Yeah, depending on the material, electrons can travel either slower or faster, and this table tells you. All right. How are we doing so far? I forgot to stop in the middle to see if anyone was confused. I mainly didn't stop because the beginning was a review of current, voltage, and resistance. Who's Royale? Is that Anaya? Who's Royale? Oh, Tahira. Royale is Tahira. Okay. So again, as you run electricity through these wires don't just accept these electrons without any resistance, right? As you run electrons through a wire, through a circuit, you experience resistance, right? So the circuit itself is slowing the electrons down. What about the circuit? The rectangle itself wiring? It's like in the wiring. Wiring. What do you mean? What do you mean by isn't the rectangle itself wiring? Is it a wire? It could be. It could be anything that connects. It could be any conductor, right? Any conductor can be, yeah, it could be. So, all right. So, okay, let's go over it again. Yeah, it's a general term. I think, hold on, I'll show you the circuit board we would use. If we ever come back to school, this is a circuit board we'll use. So that's a circuit board I think that's a circuit, yeah, that's a circuit board we'll use. The circuits is anything connecting whatever points there are. So for example, this thing right here, these lines, those are circuits. Whatever is in them, those are circuits. But we're more talking about wires. We're not talking about circuits themselves right now. We're just talking about wires. What is a conductor? A conductor is anything that allows movement of electrons. The resistor would be maybe if you connect a lamp here. So if you connect a light bulb in one of these sockets, that would be a resistor, right? If you connect three light bulbs, there are three resistors. And this is where you would connect a light bulb. That's where we would if we had lab. Also, all lab requirements are waived, by the way. If the regions are still held, all lab requirements are waived. Why are they considered resistors? Oh, why are the wires considered resistors? Or why are wires considered resistors? Why is the what it would be considered a resistor? Hold on. Yeah, the wires themselves slow down the rate of transfer. Yeah, yeah. You also see that the resistance is also very low because these constants are 10 to the negative 8. And the wires themselves, their cross-sectional area is very low too. Because the resistivity constants are 10 to the negative 8. Are you sure you're fine, Rosita? I can answer more. Maybe at the end. And that, so again, this is a wire, it can be anything, can be a circuit. So this is the formula to calculate resistance across a circuit or wire. Now let's talk about temperature relationships. So if you increase the temperature, atoms are going to start vibrating more. All right, atoms are going to start vibrating more if your temperature increases. And so these blue dots right here are atoms. Now, as you increase the temperature, what's going to happen is that because the atoms are vibrating more intensely, electrons are going to have a harder time traveling through all these electrons. So you see on the left hand image right here, at a low temperature, you see that at a low temperature, these atoms are relatively stable or still. They're not really moving a whole lot, and so these electrons can flow through each of these atoms at a relatively easy pace. But as you increase your temperature, these atoms are starting to vibrate now, vibrate much more intensely. And that causes the electrons to have a little bit more difficult time of passing through each atom, passing through the wire. So there's a reason why on your reference table it says resistivities at 20 degrees Celsius. The reason being is because as you increase your temperature, this resistivity increases as well. So as you increase the temperature of a wire, of a current carrying wire, you're increasing the resistivity. All right. And this doesn't really work out the same for batteries because there is a certain operating temperature for batteries that makes it the most efficient. But wires, if we're just talking about wires, we only care about uh this is the relationship you want to have. You don't calculate resistivity in high school physics, but there is a way to do that. Yeah, there is. Does the resistivity increase proportional? Hold on. I think no. I think it's an inverse relationship. It's like 1 over. I don't know for sure. I think it's definitely inverse, right? It's definitely inverse relationship, but I'm not too sure. Batteries work differently. Batteries, you want an optimal flow of electrons. The the fact that charge, okay, not batteries themselves, charging batteries. There's an optimal, well, okay, using batteries too, I guess. You don't want the temperature to be too low because the flow of electrons through the battery itself is slower. It's just a different battery chemistry. So it has something, there's something to do with chemistry of batteries that I didn't really study too much on. I didn't really focus on electrical physics, electromagnetic physics at least. Hold on. I know where to find this information. Give me a second. It's it's an inverse. It's an inverse relationship. So it depends on electroconductivity as well. Here. Yeah, no problem. It's fine. Let's go do the homework now. Let's do the homework now. Actually, most of these homework questions are conceptual. A lot of them are. So let's actually go to one. So an aluminum wire of length 1 meter. Okay, length 1 meter. So again, it's conceptual. So a wire of length 1 meter has a resistance of 9 times 10 to the negative 3 ohms. If the wire were cut into two equal lengths, each length would have a resistance of what? So let's take a look at this formula right here. Right, that's your formula. So the only thing you're doing here, if your R is the same, well, you still have to explain it, Tommy. If R is the same, then, well, if you have L, well, what does this become? Well, you just made the whole entire thing half as well. So your original resistance is 9 times 10 to the negative 3 ohms. And if this problem says if you cut the length in half, if you have this length, well, then you just have the resistance right here because of this, right? We just made it possible. So if you have your resistance, you're gonna get this number right here, and so the answer would be B. The answer would be B. Number two. Number two is also a conceptual question, and you have to be careful about this. It says compared to the resistivity of a 0.4 meter length. So again, resistivity is your resistivity. Length of 1 millimeter diameter copper wire at 0 degrees Celsius. The resistivity of a zero point 0.8 meter. All right, I'm sorry. All right, Joshua, you still on one, right? Do you still want me to explain more on one? I'll go back to one. Just let me know. No, you can't just guilt trip me like that. You can't just say you're moving a little fast and like, nah, never mind, I'll do it myself. You can't just do that to me. All right, let's do this again. All right. So again, you have this formula over here. You have this formula over here. All right. And now again, they say your resistance is 9 times 10 to the negative 3 ohms. Okay. And it says if the wire was cut into two equal lengths, each length would have a resistance of what? So all you're doing here is you're having this L by 2. So so that becomes, well, I'm not doing this. I don't care about this. Right? So R is equal to P 1/2 L divided by A. And if you solve this, you get 1/2 PL over A. So what is the resistance now? Since your new resistance is 1/2 R, well, all you're gonna do is 1/2 this number, right? All you're gonna do is have this number right here, and you get 4.5. Joshua, are you okay with why I put 1/2 L here? You're cutting the wire in half. Yeah, sure, Jawad. I'll go over it later. After all this, after 7C. No, because you're having your length, that means everything else is halved well, because now you finish carrying it over, and so your resistance is also going to be halved. All right. So each length would have a resistance of half of 9 times 10 to the negative 3. So 9 times 10 to the negative 3 times 1/2, you get 4.5 times 10 to the negative 3 ohms. And so that would be your answer. So now let's do number 2. And again, so number 2 says compared to the resistivity. Again, they want resistivity. They want resistivity at 0.4 meter length of 1 millimeter diameter copper wire at 0 degrees Celsius. The resistivity of a 0.8 meter length of the same diameter copper wire at 0 degrees Celsius is what? So again, you're going to take a look at this. So you don't really even need to take a look at this actually. So it's the same copper wire. It's the same exact copper wire. That means that even though your lengths are different, P is the same. You have the same temperature as well, right? You're still at 0 degrees Celsius, so you're not changing at any point. You're still copper. The resistivity of copper is also still the same. It's still copper, the material isn't changing. So even though if the length changes, sure, R changes, right? Your resistance will change. If L changes, that's what the question is saying since it says your length changes. If your length changes, resistance will change. But P is more or less a constant at a certain temperature. And that's what the question is asking for. They want the resistivity. So your resistivity stays the same. It doesn't change unless you increase the temperature or change the material. So unless you are changing the material or increasing temperature P resistivity doesn't change. Yeah. Resistivity is something completely different than resistance. It's every material has its own constant. Right? It has its own innate difference. So resistivity is something completely different than resistance. Well, it's not completely different. In terms of variable, it's completely different. But it's more or less a constant at a certain temperature. How are we doing so far, guys? I'm actually going to go through all these homework questions. Oh yeah, Alicia, did you read my comments on your previous homework? Well, the diameter will matter. Yeah, because that's how you calculate cross-sectional area of a circle, right? A circle is an area of a circle is nr squared. And so if you have one diameter, 1 millimeter diameter, take half of that diameter and solve for area. Yeah, but your diameter does matter. But in that question, it didn't matter because we didn't care about resistance. We only care about resistivity. So number 3. A tungsten wire has a resistance R at 20 degrees Celsius. The second tungsten wire at 20 degrees Celsius has twice the length and half the cross-sectional area. Yeah, and to get MA yeah, you just divide that by 1,000, Alicia. Yes, Tommy, I returned it, didn't I? So let's do 3. So has twice the length and half the cross-sectional area. So the second tungsten wire has 2 times the length and 1/2 the cross-sectional area. So in terms of R, the resistance of the second wire is what? So the first wire has L, first wire also has A, and so that formula for it is this, okay? And now the second wire, so this is the second, and this is the first. So the second wire would be this. And so you plug in 2L for L. So let's actually move this to the other side. P, 2L, a 1/2 A. Okay. And you finish solving for these numbers, 2 divided by 1/2 is going to give you 4. If you don't trust me, you can use a calculator. So 2 divided by 1/2 gives you 4. So you get 4PL over A. So the second wire has 4 times the resistance of your first wire now. Okay, because you see 4 here. So it has 4 times the resistance of the first wire. So the answer is D for R. Please ask me questions about this. I know this can be confusing. Substituting, I know conceptually it's confusing because you guys have a lot of trouble with conceptual questions. And that's not an understatement. I think that's not exaggeration. Definitely not exaggeration. Everything's confusing to you. Yeah, so the higher the temperature, the higher the temperature, the higher resistivity. And because the higher resistivity, you get a higher resistance. All right. How are we doing so far? Let's move on to 4. Let's see. You Miss Chen? There's only one Miss C I know about. Number 4. After an incandescent lamp is turned on, the temperature of its filament rapidly increases from room temperature to its operating temperature. As the temperature of the filament increases, what happens to the resistance of the filament and the current through that filament? So if you guys don't know what a filament is, it's actually I'll show it relatively easily. So that's what a filament is. I mean, not the filament. That's what a light bulb is, and the filament is basically whatever allows electrons to travel through. So the circuit is right here. Electrons travel through up here, goes through here, and lights up the light bulb, and then goes back down and to the other part of the circuit. All right, so that's the part the electrons travel through. So that's what they're talking about. The filament is this is the filament. That's what they're talking about. So as you increase the temperature, which is what the problem is saying, as you increase the temperature, you are increasing the resistivity. All right. I can't tell how late you are, Alicia, to that. I can't tell whether or not Alicia's like on the live button or not. All right. But so as you increase the temperature, so increase temperature, your resistivity goes up. And if your resistivity goes up, well, if you take a look at this formula up here, or rather down here or over here, if your resistivity goes up, then R must go up. So as your temperature increases, your resistance increases. But what about your current? What about your current, right? What about your current? So there are two ways to answer that. One is a conceptually. If you increase your resistance, by definition, you are slowing down your electrons. So if you increase your R, if you're slowing down your electrons, that means you're decreasing your current. So that's how you can think about it conceptually. The other way to think about it is using a formula. Okay? So if V stays the same and R increases, then I must decrease. And so if you can't see that conceptually, let's put numbers to it. So let's put 1 is equal to 1 divided by 1, or rather 2 divided by 2 divided by 2. So if I raise this 1 to 2 and my voltage stays the same, if my V stays the same, well then I must decrease. Okay, so if resistance goes up, I must come down. And then so you can either think about it conceptually or you can just use a formula to think about it and numbers. So the answer is A. 5. Before I move on, are we okay with number 4? All right. I think you guys have a 10-second delay. Maybe it's because of your internet, but when I watch myself, it's a 5-second. Uh, so let's say electrical resistance of a metallic conductor is inversely proportional to what? So they want an inverse proportion. So what they mean is that they want this. So as something decreases, your other side increases, right? So that's what they want. So let's take a look at this formula. And we kind of talked about as something decreases, the other thing increases in the previous in number 4, where I did R is equal to V over I. So if R increases, then I must decrease. So whatever on the top increases, the thing on the bottom on the other side must also decrease. So that's inverse. This is inverse proportion. All right, there's an inverse proportion here. So let's take a look at 5a, temperature. As your temperature increases, as temperature increases, then resistivity increases. So as temperature increases, resistivity increases. Well, if you have something on the top increasing here, then R must also increase. Okay, so if you want to think about it this way, let's do 1 is equal to 1 times 1 over 1, right? So if P is 1 and you raise it to 2, again, we're increasing number 2 here. Well, this number right here, it's not going to be 1 instead, it's going to be 2. So increasing your temperature, increasing your resistivity increases your R. Actually, I don't want to raise the whole thing yet. So 5a can't be right. 5b says length. Well, it's the same logic we did with temperature. If something on the top is increasing, that must mean R must also increase. Okay, so there's no way length can be true. Cross-sectional area, we're getting a bit closer now. Now we're going on the bottom. So if your cross-sectional area, so if R increases, P must increase or L must increase. But if your number is on the bottom, if your variable is on the bottom, that must mean that as R on the other side increases, your cross-sectional area must decrease. And we can prove this. And if you can't see this conceptually, we can prove it by using numbers. Okay, so let's say R is 1. Okay, so R 1, 1, 1. So if we decrease area, let's say 1 is now 1, 1, like 0.5. The answer you're going to get, 1 times 1 is 1, divide by 0.5, you get 2. So if you decrease your area, you increase your resistance. And that's what they want. They want an inverse proportion. Inverse proportion means that as something increases, the other thing decreases. That's what inverse proportion means. All right, so that's what they want. So the answer is C. The answer is C. And let's rule out choice 5D as well. So 5D says resistivity. We talked about that with in A. So temperature and resistivity, they're the same thing, basically. Increasing the temperature increases resistivity. So 5D is definitely not right. So the only answer is 5C. I think that's the hardest problem on the on the homework actually. It really is. Yeah, I don't know why you guys have problems with conceptual questions, but you guys do. I don't know why, but you guys do have problems with it. Let's do 6. It's something I want to solve, like figure out why you guys have trouble with conceptual questions. Well, I can see how it doesn't make sense, Arissa. You kind of arrived like really late. Well, I guess there are a lot of factors to think about. Um, but I'm gonna move on to 6 now. So I'm gonna skip the top part right here. So it says a piece of wire. The piece of wire that has the greatest resistance is what? So again, we're gonna take a look at this formula right here. We're gonna take a look at this formula right here. So they want something that gives you the greatest resistance. And they want something that gives you the greatest resistance. Again, if you can't think about this conceptually, use numbers. All right. So I'm gonna ignore P because all these wires are at the same temperature and they're the same material. They're all copper and they're at the same temperature. So I'm gonna ignore P here. I will make this simple for us. I'm gonna do L over A. So R is gonna be L over A. Again, I'm ignoring resistivity. I'm ignoring P because if it's the same temperature, if it's the same material, they all have the same resistivity. So L. Now, let's take a look at wire 1. Wire 1. Wire 1 is just L over A. Wire 2 is 2L over A. So that already gives you 2. So wire 2 has double the resistance of wire 1 already because you have 2 here on the top. Wire 3 is 1L over 2A. Tommy, you can Google it. Google physics reference table. And so wire 3 is 1/2. So when you solve this, this becomes 1/2 L divided by A. And wire 4 is 2L over 2A. Also, Tommy, I didn't mean that in like a really passive aggressive way. I apologize if I sounded like that, if I sounded mad. 2L divided by 2A gives you L over A. So wire 1 is L over A, so that's 1. Wire 2 is 2 times wire 1. Wire 3 is 1/2 wire 1. And wire 4 is the same as wire 1. So the one that gives you the greatest resistance is wire 2. Because, yeah, the one that gives you the greatest resistance is wire 2. Ask me any questions about this that you don't understand. Please. Actually, I want to rewrite this. Give myself more space. Yeah, for the most part, because it's on the bottom, right? It's inversely proportional. So I rewrote it. So if you take a look at this, since you know R is L over A, Since our resistance is length over area, and you solve for all of this, you get 1 for resistance for wire 1, 2 for resistance for wire 2, 1/2 for wire 3, and 1 for wire 4. So the one that gives you the greatest resistance is going to be wire 2. It's going to be wire 2. Because if you think about it, the longer you make a wire, the more there's a greater path for electrons to travel, right? So electrons are gonna bump into a lot more things as you increase the length of a wire. So there's a greater resistance. And as you make the area of the cylinder smaller, there's less room for electrons to go. So there's even a greater resistance, right? So electrons can't even move as much now. So increasing length and decreasing your area reduces the room. For one, it increases the path electrons have to take, so there's greater resistance, and you're decreasing the room for electrons to travel by decreasing the area. That's how you can think about it. You can either think about the math way or like the conceptual way. I like this because I only do this for physics, and everything else is like menial work. Someone else is doing my earth science class. That I'm happy about. Yeah, unfortunately, Alicia. So this is one you're gonna be using your reference table. This is an earth science reference table. So at 20 degrees Celsius, 4 conducting wires are made up of different materials and have the same length and same diameter. Which wire has the least resistance? So, assuming that your length and area stay the same and the temperature stays the same, what gives you the greatest resistance, or rather, the least resistance? So, out of these 4 choices, you're going to look for the one with the lowest resistivity, and the lowest resistivity will give you the least resistance. So let's look at aluminum. Aluminum and gold. Let's compare aluminum and gold. 2.82 times 10 to the negative 8. 2.82 times 10 to the negative 8, that's the least resistivity. So aluminum has the least resistivity right now. Uh, oh god, I made a, yeah. It's least resist. So there's the lowest resistance here. So this is least resistivity. So let's compare aluminum and nichrome. Well, 150 is definitely greater than 2.82. Wait, hold on. I'm confusing I'm mixing myself up. I'm sorry. Gold has a lower resistivity than aluminum. I knew I was right. I was second guessing myself. So since 2.44 is lower than 2.82, gold has the least resistivity and as a result has the least resistance. So gold is so far the least. And then you compare gold to nichrome. So comparing gold to nichrome, 2.44 is definitely less than 150. So gold has the least resistance. Gold has the least resistance so far. And now you want to compare gold and tungsten. 2.44 is less than 5.6. So gold definitely has less resistance than tungsten. So gold is the answer. Thank you, Tommy, for letting me know. So gold is the answer for number 7. So again, you're basically the only thing you're looking at is you're looking at your reference table and you're figuring out which one has the lowest resistance. Yeah, pretty much. Because you know that if you take this formula right here, you know that if P decreases, R increases, and if P decreases, then R decreases as well. All right, see ya, Tommy. Change your profile pic. Now 8. What change decreases the resistance of a piece of copper wire? So which change decreases the resistance of a piece of copper wire? So you're taking a look at this. Now, Arissa, watch the lesson video. It's the lesson video on Google Classrooms is 27 minutes long, and it's much shorter, and it explains all the homework questions as well. But I'll explain everything to you after I'm done with this. Let's take a look at 8. Oh yeah, Alicia, I was talking about Tommy, because Tommy has a very inappropriate profile pic. Then yeah, Tommy has a very inappropriate profile pic on on his school Gmail account. Number 8 decreases the resistance of a piece of copper wire. So you want to lower your resistance. Well, we know that if we want to lower our resistance here, we want to lower our resistivity on the top. We can lower our resistivity on the we can lower our length on the top. But if we lower our resistance on the side here, A must decrease. A must increase. So let's take a look at 8A. Increasing the wire's length. Well, if you increase the wire's length, if you increase length, then R is going to increase. So A can't be right, right? Because if I change this from 1 to 2, then this side is going to change this side is going to double as well. Increasing the wire's resistivity. Well, again, on the top, if you increase the resistivity, you increase the R. So B can't be right. Decreasing the wire's temperature? That could be. Because if you decrease your temperature, you decrease your resistivity. And if you decrease your resistivity, you decrease your resistance. How are we doing so far? So again, for now you can think of temperature and resistivity as proportional. So if temperature decreases, then resistivity must also decrease. Alternatively, if temperature increases, resistivity must also increase. So again, if you thing you have on the top decreases, then on this side this must decrease. If the top increases, this side must increase. But it's inversely proportional to this. It's kind of like this. That's kind of what that means, and on the graph, that's what that is. So y is equal to 1 over x. So that's what you see on the graph in math. So the answer would be C. So which chain decreases the resistance? Well, if you decrease the temperature, you decrease the resistivity, you decrease the resistance. Let's take a look. All right, Joshua, let me explain the difference between resistance and resistivity. Resistivity is more of like a constant because resistivity is measured. Resistivity is more measured in ohms times meters, right? So depending on the material, whether or not it's a lithium, aluminum, copper, gold, nichrome, silver, tungsten, the resistivity of the object will change, right? Each material has its own innate resistance, innate resistivity, that it doesn't want electrons flowing through them, all right? So maybe some people can handle eating spicy food really well, so it goes through the system really well. But maybe some people assholes are probably gonna burn if they eat it. So it's kind of like that. Every person has their own innate resistance to spicy food, and each material has their own innate resistance to electrons. Okay, so some of these materials don't want electrons flowing through them, and as and resistivity is on your reference table. And as a result of these different resistivities, your resistance changes. So again, resistivity is PL over A. Who is wannabe loser again? I forgot. Uh, so resistivity has to do with more with the material. Resistance is just how well they resist electrons. So again, resistivity is how well the material resists electrons, and R is basically overall resistance. Resistivity is a constant, uh, basically. Yeah, resistivity is just a constant. It doesn't really mean anything. Uh, Roy Tahira, what is your question? What are you confused about? Hello? What do you mean that's it? I finished 8. Yeah, yeah. I've been going on for like an hour now. Yeah, that's it. Now I'm just answering questions. I'm probably yeah, I'm just answering questions now. You know nothing at all. Well, let's start from the beginning. Did you understand electric current? Arisa, the answer, you can scroll back in the video. You can look through the video. You stay safe too, Prince. Tara, how are you doing on electric current? Joshua, I believe in you. You can figure it out. Why am I being a day room? Arissa, come on. Can't just. I would give you. I would. You gotta be here on time. But Tira, Can you tell me how you're doing on electric current? Do you understand what electric current is? I'm pretty sure I understand what she means. Do you understand what electric current carries? A water current carries water. What do you think electric current carries on the most fundamental level? You guys are kids, enjoy being kids. Come on, come on. Electrons. Electrons. It carries electrons. So electric water current carries water, electric current carries electrons. And those moving electrons is electricity. Okay? How are we doing so far? 'Cause because that's what electricity is. Electricity is the movement of electrons. And so if you have a high water current, the water is traveling really fast. So if you have a high electric current, your electrons are traveling really fast. So so the faster your electric current is, and that's basically what electric current is, how fast you're carrying these electric electrons through a certain point. So let's talk about voltage. You understand what voltage is? Tahira, say one in chat. 10-second delay, which is fine. All right, let's talk about voltage. So I want you to think of voltage as water pressure, right? I want you to think of voltage as water pressure. So the higher voltage you have, the more water pressure you have. Okay, and the higher voltage you have, the more electrons you have. So if you have a high water pressure, you have a lot of water, and a higher voltage, you have more electrons. I'm never using Google Meet. Never, never. And lower voltage, and if you look on the bottom, if you have a lower voltage, you have less electrons. So if you have less water, you have lower water pressure. And when you connect these two voltage, there's a potential difference here. There's a voltage difference. And so all this water from the top is going to come streaming down because naturally it will. It will want to even out. So because you have a higher voltage here, you have more electrons here. Electrons are going to flow from the high voltage area to the area with lower voltage. And that's how your battery works, right? So in your battery you have a negative side and a positive side. The positive side doesn't have as many electrons, and the negative side has a lot of electrons. So the negative side of your battery pushes electrons to the positive side. And that's how you have appliances running things. So But if you run your electrons through anything, there's a resistance through the material or through a light bulb or through whatever thing you're running electricity through. And so that's this dam right here. You can think of resistance as a dam, right? Because the dam still allows electrons to flow through, but the dam decreases the rate at which it flows through, right? It slows it down. If this dam wasn't here, all this water would just come rushing to the bottom. But because there is a dam here, you're slowing down the flow of water. So a light bulb, a refrigerator, your Xbox, my Tesla, slows down the flow of electrons. Okay? Whatever thing that uses electricity, it's being slowed down. It slows down electrons. Okay? And so that's what a resistor is. We call those things resistors. Right? Your PS4, your TV. Gotta bring some, because that seems to draw your attention. So again, in this circuit diagram, you have a resistor. And this resistor can be anything. Anything that uses electricity. It can be a light bulb. It can be your AC, right? It can be your phone. Anything that uses electricity. It can be your hair dryer. It can be your uh what else? What's sort of other things that use electricity? Anything that uses electricity can be a resistor. And it applies the resistance. Okay? So it slows down the electric current. So, and not only do appliances cause resistance, the wires themselves, whatever is traveling through, the wires themselves cause a resistance as well. I'm trying to Google like a wire. Sure, this works. So let's take a look at this wire. All these wires, if you run a electric current through any of these wires give a resistance. No, that has nothing to do with it, Joshua. It's no, yeah, that's nothing to do with it. The reason why batteries don't last as long is because just the battery chemistry and how what their cells inside get how they get damaged over time or how they don't accept electrons anymore. But resistivity is nothing to do with that. But so you're more and this formula that you're learning today has is more we're more concerned about the current running through these wires, right? And the resistance that each of these wires uh, give for these electrons. So all these wires, there is some innate resistance to flow of electrons. And so the formula for that, so the formula for that is this, right? R is equal to PL over A. And so L is the length of the wire, A is your cross-sectional area, P is a resistivity. P is specific to the material. Each material has a different resistivity. And so that's P. And so R is resistance, so R is equal to PL over A. And again, if you take a look at this, there's a temperature relationship here. So if you increase the temperature, what's going to happen is that your atoms, these blue atoms, are going to start vibrating. And when they vibrate more, electrons have a harder time moving through all these atoms. So as you increase the temperature, you're increasing resistance. You're slowing down the rate at which electrons flow. Okay. So that's how temperature relates to resistivity. As temperature increases, resistivity increases. I don't want to explain this twice because I'm running out of breath and I want I want to stop talking. If you need help answering the questions, I would look at the video I posted. Yeah. Ursa, when you turn stuff in, can you order the numbers? Like I don't want to see number 3 in the middle, number 1 in the top right hand corner, number 8 in the bottom left hand, number 5 in the top left hand corner. Is Arista even here? Oh, probably not. Each wire. Each wire. I mean, collectively, you have to add up. Yeah, yeah. Each wire. Companies, when they're manufacturing these wires, they probably know how much wires are in them, so they probably just say the resistance as a whole. They give you the resistance as a whole because they know how many wires are in them already. So I'm not too adept on that. That's what I would assume. Again, this is a formula for resistance of a single wire. So wires in wires in uh wires in a circuit. Wires in a circuit, or wires in that each of those strands of wires are in parallel. Okay, so you calculate resistance differently because they're in parallel. We'll talk more about series and parallel circuits. We talk about series circuits on Friday, parallel circuits on Monday. But those strands of wires are something we call parallel circuits, and so you calculate resistance differently. If you want to take a look at it right now, if you take right here, resistance is calculated like this in parallel circuits. All right, see you, Joshua. All right, if there are no more questions, I'm gonna go. See you later, Alicia. Are your questions answered, Rowita? No, it's fine. All right, see you guys.